Okay, we're asked to calculate all the final concentrations in a system where we're taking potassium oxalate and reacting with barium bromide. That's going to give us barium oxalate plus potassium bromide. Okay? So let's begin with the potassium oxalate. And let's calculate the easy ones first, all right? So all right. So if my concentration of this is, I've got 0.1 liters, all right, and it's 0.2 molar. That means I'm going to have this many moles of the potassium oxalate. That completely breaks apart, and according to the ratio, I'll end up with twice as many moles of the potassium as the oxalate. Okay? Now we can go ahead and just calculate the concentration of the potassium right away. So I've got 100 mils of the potassium oxalate, and I'm going to be adding 0.15 liters of a 0.25 molar solution of the barium bromide. So in total, my volume is going to be 0.250 liters when all said and done. So the concentration of the potassium will be 0.16 molar. Okay. Let's not forget about the oxalate over here. We'll tackle that at the end. That's going to be the tougher one, okay? Let's go on to figure out the amount of bromide. So I've got 0.15 liters of a 0.250 molar solution. Whoops, wrong one. Barium bromide. It'll completely break apart because it's a halogen. So how many moles of the barium bromide do I have? Just multiply the volume by the molarity. All of that will break apart, and I'll end up with 0.0375 moles of the barium. And I will end up with twice as much moles of the bromide. And then I'm going to divide that by my new volume, 0.250 liters. So this comes out to be a 0.30 molar solution of the bromide. Okay, so we got two of them done. Now what we need to do is look at what will the concentrations for the barium oxalate be? So what we can do is, let's see, is there a faster way to do this? Well, we can make a lucky gamble. Let's just say that, let's just calculate the concentration here. This is 0.15 molar of barium. Okay, this is the initial concentration. Let's go back up to here. Wait a minute, did I divide by the right thing? Yeah, I did. Okay, of the oxalate. So the KSP, let's write the equation. So the barium oxalate, most of it will stay as a solid, only a little bit will dissolve. We know the initial concentrations of these. If we go back and look, 0.15 molar for the barium and 0.080 molar for the oxalate. What we need to know is whether or not Q is greater than KSP. Looking at these concentrations look fairly big to me. For something that's a solid, usually they only dissolve a little bit. So I am just going to go ahead and say that these two numbers, I'm just going to guess that Q is greater than KSP. Okay? If Q was less than KSP, then these would be the answers. Okay? But I am going to guess that we're actually in this situation. Okay? If we're in that situation, we almost really don't need to okay, well, okay, you want me to calculate Q? Fine, I'll calculate Q. So Q is going to be concentration of barium, concentration of this. You plug in those two numbers. .0120, and guess what? That is greater than the KSP, which in the problem is 2.3 times 10 to the negative 8. So I know then that I'm going to get a precipitate. And so the maximum amount that can be produced, the maximum amount, I should say, that would be dissolved will be, according to this, the KSP is 2.3 times 10 to the negative 8th. So I'm going to solve for x. That's the maximum molarity of those two. Because anything above those molarities are going to precipitate. And the problem didn't ask us to calculate how much precipitated. They just wanted to know the maximum concentration of the C2O4. So these two concentrations will continue to decrease until nope, I screwed up. We have to work out an ice table. So these are our initial concentrations. Everything I said is right, but because they start off at different amounts, we have to work an ice table. So if the original concentrations were the same, if these two concentrations were the same, I'd be right, what I had said. But they are not the same, so we need to work out an ice table. So KSP is equal to the concentration of barium, concentration of this. My KSP is 2.3 times 10 to the negative 8th. My equilibrium concentration is this. My equilibrium concentration here is this. All right. We cannot get rid of the x's. They are not too small. We must use the quadratic equation. So we're going to have to distribute this. Okay. I'm going to rearrange this. Okay. And now we're going to have to use the quadratic equation. So let's go ahead and plug in the numbers. And let's see what answers we get. So one possible answer I got was this. And the other possible answer whoops, no, I goofed that up. Okay, here's one possible answer I got for x. And the other possible answer is this. So those are my two possible answers for x. So the top one cannot, the 0.165 cannot be right, because that would mean, where'd my ice table go? It would mean that this number here, this concentration, would then end up being less, the molarity would be negative. So that can't be. So this must be the correct number. So 0.15 minus 0.0648, that's going to give me the concentration of the barium. And then for the oxalate, okay, so you did have to work this out like a normal ice table. So they gave you the initial concentrations. You're going to shift right, and then you plug it into an ice table. You could have done this faster if they had given you the equal concentrations of both. Then you could just go straight to the KSP equation and you wouldn't have to do an ice table.